Right, so we're looking in logarithms in the section on logarithms. We've done lots of work on logarithms now. We've been working with these laws of logarithms, you know, the product law and the product law where you can split and add, the division which leads to subtraction law, the plog, and one or two other identities of logarithms. Change of base logarithm, quite important. What I want to look at now is well, a couple of things really. Firstly, I want to touch on this kind of magical function, this y equals e to the power of x, which, right, this value of e here, equaling 2.71, etc., going on forever. The value being so important because when we look at the derivative, the gradient function of y equals e to the x, we get exactly the same function. So we get that the y dx is also equal to e to the x. So if we and it's intuitive, you know, it's if you think it through, really flat down here, really close to zero values for the function. It starts to increase, so does the gradient. So as the gradient increases, as x increases, function value increases exactly the same rate as the gradient. So it's this only for this value of e does it fit perfectly, does it match perfectly. Okay, so that's the significance of e. Just want to have a little look at what happens when we reflect across y equals x. I'll just extend this down. So I reflect that across. So 0, 1 becomes 1, 0. So that point goes over here. Now these points that are really in close here become really in close down here. We go through 1, 0, and then we get further out this way. So this is the inverse function for y equals e. For the function of y equals e to the x. All right. So if we look at this algebraically, y equals e to the x, what is the inverse function? So if we switch the coordinates around, we log in, we end up with log base e of x is equal to y. So therefore, my inverse function is equal to log x to base e. So if my function is e to the x, my inverse function is y equals log base ex, which is also referred to as the natural log, or sometimes written, or quite often written, or more often than not written, as y equals ln x, meaning log base e. Okay, what else we can look at here is, well, okay, there's a nice little relationship between those. We've introduced e as a concept, how it's used, and now we can see how it's used in calculus. So if we look for the derivative, the derivative of e to the x and ln x. Okay, so if we look at, well, we know that when y equals e to the x, my derivative function is e to the x. But what about when y equals log base ex? Now, what you'll find is that as I go through this work, I don't tend to use ln. I like to see it as log e. What is y dx equal to here? So that's one to explore. Well, let's do that exploration, because what I know here from this statement is, if I log out, is that x is equal to e to the y. And I do know what dx to y is under these conditions. It's unchanged, it's e to the y. I don't want dx to y, I want dy dx though. Remember, I want dy dx, so I flip it around the other way, 1 over e to the y, but e to the y is equal to x. So in terms of x, my dy dx is equal to 1 over x. So this is important. For the natural log of x, the derivative is 1 over x. For y equals e to the x, unchanged. Okay, so how does this then translate to when I have functions of x? So let's say I have, how about y equals e to a function of x, or y equals log base e function of x. All right, so how about that situation? Well, we can use the chain rule. All right, so if it's y equals e to the fx, we can say for y equals e to a function of x, all right, we can let that function of x equal to, say, u. So therefore, we've got y equals e to the power of u. I want dy dx. So how about y equals e to the function x? What I'm asking here is, what's the derivative? What's dy dx for when it's e to the fx? So I want dy dx, and dy dx is equal to dy du by du dx. Dy du, well, I've got y equals that, so dy du is this equal to e to the u. Du dx, well, if u is equal to the function of x, then du dx will just equal f dash x, won't it? So this is f dash x. So what I end up with is f dash x e to the u, where u is equal to the function of x. So we end up with this nice little result here, where if we've got, let's have a look at an example, derive y equals e to the power of 3x plus 1, then I can use this result here to say, right, if I start out with this function e to the function of x, then the derivative is f dash x, so the derivative of that index, which is 3, by e to fx, as it was in the beginning, so 3e to the 3x plus 1. Okay, how about when we have, all right, so for y equals log of function of x, all right, similarly we'll let f of x equal to u, so therefore y is equal to log u. I know that dy dx is equal to 1 over u. I've just found that up the page a little bit. So therefore dy dx will equal dy du by du dx. Now dy du is it's just here, dy du is 1 over u, du dx is f dash x. So what I end up with is f dash x over u, which is f of x. So for a log function, let's do an example. Therefore, derive log base e 1 plus x squared. All right, so what we end up with there is log base e 1 plus x squared. Let's have a look here. Log of a function of x derives to f dash x, so I'd take the derivative of that function, which in this case is 2x, and I put it over the function itself, 1 plus x squared. There we are. So we have, there's my derivative for the log function 1 plus x squared. Okay, I'm going to leave it there. We've got lots of practice on these questions. I've only given a couple of very straightforward examples. There'll be more interesting things in the textbook, but we're pretty ready now to move on, and we can work right through now to exercise 5M, right through to exercise 5M. So I think that leaves you to do J, K, L, and M. And I think the target there is by the exit. So I'll see you in class, and we'll do lots of questions, and you'll be able to work these through product rules and quotient rules, and bring in some other areas of the course as well. So see you soon.